video, we are going to cover specific reflexes in the body. Now, we've talked about reflexes can be spinal or cranial, somatic or autonomic, polysynaptic or monosynaptic, ipsilateral or contralateral. So we are going to focus on a group, specifically the somatic spinal reflexes. Now, what does that mean? Well, if it's somatic, that means the effector will be skeletal muscle, so you're consciously aware that it's occurring. And spinal means that it's going to be controlled by spinal nerves, and the integration is within the spinal cord, specifically the gray matter of the spinal cord. So the first reflex that we are going to cover will be the patella reflex. The patella reflex is a specific type of stretch reflex. And again, this is a protective mechanism. The patella is being hit with a reflex hammer. The patella tendon stretches, pulling on your quadricep muscle. And to protect the quadricep muscle from being stretched too much, it is going to cause the leg to kick or extend. So the quadricep muscle is contracting to protect it from stretching. This particular reflex, the stretch reflex, altogether will be ipsilateral, monosynaptic. It will involve reciprocal innervation, and as stated earlier, it's a somatic spinal reflex. So these are all things you want to keep in mind. Also remember that all reflexes are going to be composed of 5 components in the arc: receptors, sensory neuron, integration center, motor neuron, and effector. So, in the stretch reflex, we are going to be detecting stretching of a muscle. So, the receptor, the sensory receptor, is known as a muscle spindle, and it detects stretching of the muscles. I kind of think it looks like lips with thread put through it. Now, notice that the muscle spindle is in the quadricep muscle for this example. So this is the primary muscle that we are focusing on. So the muscle spindle detects stretch, and it's going to send sensory input down the sensory neuron or afferent neuron to the gray matter of the spinal cord. So this is going to be the integration center. Now focus on that sensory neuron. And we're going to see that there's 2 pathways to the sensory neuron. We have pathway 1, which is right here, and we have pathway 2, which is right here. Now we're focusing on the pathway that is involving the primary muscle, which is the quadricep muscle. What we'll notice is that in the integration center, the sensory neuron directly communicates and synapses with the motor neuron. So since it's a direct communication, we only have one communication point. This is going to be monosynaptic. You'll also notice that the motor neuron exiting is solid, and it has a plus by it. This is because this particular motor neuron is going to be an excitatory motor neuron. We're not inhibiting it, we're exciting it. We're sending a signal right back to the primary muscle, which is the quadriceps. So this motor neuron is traveling back to the quadriceps, and it's going to tell the quadriceps to contract. But remember, we said this is reciprocal innervation, and because it's reciprocal innervation, it's going to involve antagonistic groups. So the quadriceps is going to cause extension, and the hamstrings will cause flexion. So if the quadriceps is contracting, we need the hamstrings right here to relax. So you'll notice that the secondary pathway is going to have a dotted line, which is a motor neuron going back to it. That dotted line also has a negative sign next to it because we're inhibiting this pathway. We don't want the hamstring group to contract at the same time the quadricep group is contracting. Since the muscles that we are going to, the motor neurons are going to, are skeletal muscles, it's a somatic reflex. So to review this real quickly, we have our muscle spindle detecting stretch in the quadriceps. The muscle spindle will send an afferent signal to the spinal cord gray matter integration center. Well, it will directly synapse with a motor neuron that is solid, taking information right back to the quads, and that motor neuron is excitatory, it's depolarizing, and it's causing the quadricep muscle to contract. Well, the antagonistic to the quadriceps muscle is the hamstrings group, and you'll notice in the motor pathway from the gray matter, it is a dotted line with a negative sign beside it, because that motor pathway is hyperpolarizing or inhibiting. We're not sending a signal down it, so that way the hamstring muscle says relax. This protects the muscle from being overstretched. So again, the stretch reflex is somatic spinal, monosynaptic. The sensory neuron and the motor neuron enter and exit on the same side of the spinal cord, so it's ipsilateral. So this next reflex that we will discuss is going to be a little bit more complicated because this reflex is a combination of the flexor reflex, also known as the withdrawal reflex, so you're pulling a body part away from harm. So this one is a combination of the flexor reflex and the cross extensor reflex. So this reflex is going to have the sensory stimulus and the motor response on opposite sides of the body, so it's contralateral. It is going to involve multiple segments of the spinal cord, so it's intersegmental, and it's going to be a little bit longer to relay the message in the integration center because it is polysynaptic. So when we talk about this reflex, it's usually in reference to balance maintaining. So crossed extensor, it's always going to be combined with the flexor reflex. It's a balance maintaining reflex. The crossed extensor reflex is polysynaptic, contralateral, and involves multiple segments of the spinal cord, so it's intersegmental. Okay, in general, a great example is this picture. You step on something sharp with, say, your right leg. Before you can withdraw the right leg and flex it to pull it away from the injured foot, you need to have your left leg, so cross extender, straighten to hold the body weight, so that way your flexor then can lift the right foot. So as you're lifting your right foot to maintain safety, your left foot needs to extend the cross extensor portion of it to maintain your balance. Since it involves multiple muscles at different heights, at different areas in your body, it involves multiple segments of the spinal cord. Okay, so let's go over the exact steps. Okay, the first component is going to be the sensory receptors. These are going to be nociceptors if you're stepping on something sharp, which are just receptors that detect pain. And they're going to send a signal down an afferent neuron, so a sensory neuron, through the back of the spinal cord to be integrated into the gray matter. Now, what we want to do is our outcome is to basically flex this right foot, or the right leg, to bring the foot away from danger. But if you do that, you're going to fall straight on your face. So at the same time that you're flexing the right foot, you want to extend the left leg. So what we'll notice is that the sensory neuron right here is going to communicate with multiple interneurons. Many of them are going across the spinal cord and communicating with motor neurons on the opposite side. So that's where the contralateral comes in. Since the original sensory neuron is communicating with a interneuron before the interneuron communicates with the motor neuron, that's more than one synapse, so that's polysynaptic. Now you'll notice that it is causing your entire hamstring to contract, as well as the opposite side of the body to extend. So we're using antagonistic muscles, but we're using them on opposite sides of the body. So while one's contracting, the other one will be relaxing. So while this one flexes and closes the angle, your left leg is going to extend and put the weight on the foot to maintain your balance as you pull that right leg away from danger. Because it's targeting multiple levels of your spinal cord, it's going to be intersegmental, so L2, L3, L4. All of those segments are going to be involved, not just one segment here. It's going to be multiple segments being involved at once. So the cross extensor is a balance maintaining reflex. The stimulus is going to elicit a flexor response to pull the right foot away. These interneurons in the integration center are going to stimulate either flexion and stimulate extension on opposite legs. So the flexor reflex is occurring at the same time that the cross extensor reflex. So we have to remember that excitatory interneurons are going to stimulate extensors on the opposite leg. Inhibitory interneurons are going to relax the flexor muscles on that same leg. And this allows us to have reciprocal innervation on opposite sides of the body.